Thank you. Yeah, so thanks very much for the invitation to speak. So I want to say something about the aspects of AlphaGo that are interesting for a mathematician. I don't assume you know what AlphaGo is, although some of you do. So let me start with Go. So Go is a two-player game, played on a 19 by 19 board. As you can see on the right, these stones, white and black, are placed at these meeting points of these lines. Black goes first. That's important to know as compared to chess. The rules are very simple. So the aim of the game is to surround territory and to capture the opponent's stones. I won't go into the rules, actually, because although they're very simple, it would take me a few minutes. So the rules are simple, but the emergent gameplay is incredibly complex, and it's considered to be one of the deepest games that human beings play. And in particular, it's famously difficult for computers to play well at Go. And the fundamental reason for that is that there isn't really a good heuristic for evaluating the current board configuration, whether it's good or bad for white or black. There's no heuristic like piece values in chess to use in these kinds of algorithms for playing Go. So AlphaGo is an algorithm. It was first described in this paper in 2016, led by David Silver and Ajia Huang. This is a research team at Google DeepMind, which is an institute, AI institute in London. So it's not the first Go program, but it is the first Go program which has defeated professionals. Not only defeated them, defeated some professionals, but defeated the best humans in the world. So there's two show matches in 2016 and 2017 in which AlphaGo showed it can beat the #1 players in the world. There's a great documentary about that. I won't say much about that part of the history. I'll just note that Kurji, I think, is still the #1 player in the world. And if you look at at least according to these rankings, these ELO rankings, the current estimate is that Kurji would beat AlphaGo in 2% of games. Okay, so it's a pretty solid gap. For those of you who have looked a bit at this before, I'll just note there's actually 3 papers that describe AlphaGo. The original one, a second paper which has a slightly different architecture, AlphaGo Zero, and then a third paper in which they get a similar algorithm to play chess and shogi as well as Go. I'm actually going to describe the architecture of this second algorithm because it's simpler. But I'll just say AlphaGo for the present purposes as an umbrella term for all of them. So, why is AlphaGo interesting? In particular, why is it interesting for a mathematical audience? So the first reason it's interesting is that as a program, it's a bit exotic. So most of the information in this program is not in the form of code that humans have written, but in the form of real valued numbers, real numbers called weights. And those weights are not written into the program, but learned by some process I'm going to describe. And the reason that is interesting is perhaps most clearly described in a talk that I recommend by Peter Norvig, who's a famous artificial intelligence researcher and head of research at Google for many years. And he said that in his opinion, as a consequence of the recent progress in deep learning and its influence on computer science, that science is becoming more like a natural science. Now, a traditional program, if you're trying to understand how to construct it or what it does, you wouldn't usually think of that as a natural science problem. I mean, natural science, the tools of natural science are observation and experimentation, and of course theory. But you don't understand a program normally by doing experiments and seeing what happens. You try and reason about it using logic. I mean, in principle, in practice, you reason about it in some way that, approaches logic in the best case. But that's the kind of object that a program is. It's more like a mathematical object than an object of natural science. But AlphaGo is different. So if you want to know why AlphaGo is playing the moves that it plays or what its strategy is, Well, in principle, you know, because there's the program on your computer, and there's a bunch of numbers there. You can look at them in principle and know the answer to those questions. But in practice, you cannot. I mean, you cannot interpret those numbers to answer those questions, at least not at present, and perhaps never. That's probably a fundamental obstacle. So the way to understand what AlphaGo is doing is to play against AlphaGo. So you play, you form hypotheses, and then you test those hypotheses. And that's a process more like natural science than traditional computer science. And interestingly enough, actually that exact process has been done, and there's a book where you can read about the results, not for Go, but for chess. So this Alpha Zero, this derivative of AlphaGo that plays chess, there's now a great book called Game Changer, which describes some of the understanding that some experts in chess extracted from playing, well, observing games played by Alpha Zero. There's references at the end of the slides that contain all the papers and books I'm going to mention. And you can download these slides, I should have mentioned at the beginning, on my webpage. It was written on the first slide, but I might just put it here. That's a new kind of object in computer science, and understanding those new objects is already generating new and interesting mathematics, and will continue to do so as those kinds of programs grow in importance. There's some questions I've listed at the bottom of the kind of examples of the questions arising from the study of these new kinds of programs. And I'll just mention that already to understand AlphaGo and programs like it, you need to understand some topology, you need to understand statistics and probability, statistical mechanics, algebra, and also logic. Okay, so it's a kind of interesting new phenomenon. So I'll come back to this topic at the end, but I want to spend most of the talk just telling you what AlphaGo is and how it works. Okay, so first of all, AlphaGo is a neural network, which is a function. It takes as input a configuration of the board and gives us output, first of all, a probability distribution over moves, so the possible places to place the next stone. That assignment of distributions to board positions is called a policy. I'll define this precisely in a moment. And the neural network, in addition to the policy, outputs an estimation of the probability that the current player will win from this position. Okay, and this is, in a sense, the white whale of Go playing programs, is this estimate of the value of a configuration of the board. So, as I'll explain, this is a well-defined mathematical object. There's a unique such function which is optimal, but it's very unclear how you can actually attack approximating that object, and that's the upshot of what AlphaGo succeeds at. So a neural network has a lot of parameters, and those parameters are tuned by a process called reinforcement learning, which I'll explain. And together, those two components, the neural networks, or deep learning, and reinforcement learning, combined are called deep reinforcement learning, not surprisingly. And that process approximates a certain convergence to a fixed point of a contraction mapping. And that's the organizing principle for this entire subject in some sense. So that's what I'll explain. Okay, so the first part, I want to define a certain class of neural networks. So feedforward ReLU. ReLU stands for rectified linear unit. Neural network N with input width N, output width M, and depth K is just the sequence of affine functions, at least the data is that. I for 1 through K. So each AI is multiplication of the input vector by some matrix and then the addition of some vector. Conventionally, the matrix you multiply by is called a weight matrix, and the vector you add is a bias. Okay? So it's a sequence of affine functions, and the dimensions of these intermediate affine spaces are d1 through dk plus 1. So that's the data, and associated to that data is a continuous function from Rn to Rm, which is almost just concatenating all these affine functions, but there's in between each of them a nonlinear function, the ReLU, which simply takes an input vector and replaces every negative value by 0. Okay, so that's all that does. So this is a simple class of functions from Rn to Rm. But nonetheless, this class of functions is dense in the same sense that polynomials are dense. So recall the Stone-Weierstrass theorem says that polynomial functions defined on a compact space are dense in all continuous functions. And there's old theorems saying similar things about neural networks. The older theorems are a little bit irrelevant in the sense that they talk about a scaling limit, which is the width goes to infinity, which is actually not what people care about. They care about the depth increasing and the width fixed. So there's sort of more modern treatments of similar statements, and this is one. I don't know if this is the best such statement, but this is the one I've checked, so this is the one I feel comfortable stating. So it says that if k is compact and you have a real vector-valued function f defined on k, and I give you an epsilon, then you can find a ReLU net with widths bounded by m plus n, which is within a distance epsilon in the subnorm of f. Okay, so any continuous function can be approximated arbitrarily well by a ReLU net. Now that's fine as a theorem, but that's not a constructive proof. It's not telling you how to actually construct that approximation, just like Stone-Weierstrass doesn't tell you. So that leaves open the question of whether in practice you can ever actually find these parameters to actually construct such an approximation. So that's the hard part. This theorem doesn't really do much for you, practically speaking, but at least gives you some hope that you can find an approximation. Okay, so I want to give you a bit of an intuition for this class of functions before we go on to see how they're used in AlphaGo. So I'll just start with the very simplest example here, which is, well, not quite the simplest, I suppose, the simplest non-trivial example. So that's a depth 2 network where the intermediate dimension is 1. So that's just parameterized by 5 real numbers. And it's this function you can see at the bottom. So if you want to understand the graph of this function, clearly you should understand where the term in brackets is 0. And that's just going to be some straight line. So on one side of that line, you'll just see the value c1. And on the other side, you'll see this function, linearly increasing. Okay, so if I sketch the areas in which the function is negative with, it's supposed to be orange, and positive in blue, then you'll see something like this. Okay, that's the line given by the vanishing of that term in the brackets. Okay, so that's maybe not very interesting. But if I increase the dimension of this this middle layer to 2, you can already get this sort of infinite triangular region like this. There's more details on the slides than I'll talk through, partly because if you're entertained, you can go back and check that you believe this shape follows from the constraints I'm going to put on the right-hand side. Okay, so more interestingly is if I increase the depth to 3 and then you play around with it. Okay, so here's a shape you can construct out of a depth 3 ReLU net with these constraints I show on the right-hand side. So this is a kind of trough, right? So these areas are positive, and there's this negative trough here. Right, so as you increase the width and the depth, this starts to get very complicated. And the statement is that if you increase the depth sufficiently, you can approximate any function on a compact subset of R2 this way. Right, so that's a feed-forward ReLU network. AlphaGo's architecture is a special kind of such network called a convolutional neural network. I don't have time, unfortunately, to detail exactly what a convnet is. But basically, if you think about the space of feed-forward ReLU nets, so that's parameterized by these weight and bias matrices. On that space, I can look at a closed subspace cut out by certain equations, which set some of the weights and biases to be 0 and other weights to be equal to one another. So tie the weights in some way. And there's a particular way of tying the weights that gives you convolutional neural networks. So these networks were developed loosely based on sort of an understanding of the human visual system or the early layers, but I don't know how seriously to take that analogy. Anyway, so they've been very successful at computer vision tasks. The form that's in AlphaGo Zero actually has these additional features, which I won't describe, which came out of the evolution of computer vision methods over the period since 2016 when AlphaGo, the first version, was defined. But the broad outlines of the network are that the input dimension is as I indicate there, 6,137. Well, the 19s you can understand, right, because that's the number of rows and columns on the board. But I have 17 degrees of freedom per intersection point, which seems a bit strange. And I need to specify whether the point is empty, white, or black. So the 17 is 16 plus 1. The 1 is used to encode whose turn it is to play. And it takes the same value everywhere. So it's either 0 or 1. That leaves 16. 16 is 8 times 2. There's 2 players. So there's 8 layers, as they say. So 8 of these degrees of freedom, which are used to encode the current configuration of the board, whether there's a white stone there, and similarly 7 moves before that. Okay, so I'll come back to this a little bit later, but that's where the 17 comes from. The output dimension is, for the reasons I kind of sketched earlier, of dimension 363, so that's 19 squared. That's the number of positions you could play, plus you could pass. And these 19 squared plus 1 numbers parameterize a probability distribution. So that's the policy. And then there's this value. So that's the output. The hidden layers are pretty large. And the network is of depth 42. Okay, so that's the architecture. I mean, obviously that's a sort of broad overview of the architecture, but the paper details everything else. Okay, so that's the neural network. The neural network is trained by a process called reinforcement learning. And this gets into mathematics that may be familiar to some of you. So I need to set up the language of Markov decision processes, policies, and value functions. And then I can state the sort of core organizing principle of reinforcement learning. So a finite Markov decision process is a finite set of states, a finite set of actions. For each state, a subset of actions which are allowed from that state, a reward function, and for each state and action, a probability distribution over possible states S prime to transition into. So the way to read that is that there's an agent, an environment. S is the state space of the environment. The agent can take some actions. After the agent chooses an action, the environment undergoes some transition stochastically to some new state, and then this is repeated. Okay, so a policy is a choice of how to act in every given state. Notice sometimes this is referred to as a Markov policy because the policy only knows the current state. It doesn't depend on the previous sequence of states or actions. So it's a function which maps each state to a probability distribution over allowed actions. So delta is the probability simplex. So the space of such functions is naturally a metric space with a submetric. So what's the goal? The goal is to determine a policy which does well with respect to the reward function. So if I give you a sequence of states, S0, S1, S2, and so on, the discounted reward of that sequence is whatever reward I get in the first state plus the discounted version of the reward in the next state, and so on. Notice that since S is finite and gamma is less than 1, this actually converges. So then, suppose we fix some initial state, so I can think about many possible trajectories in state space from that initial state, following a given policy pi. So I start in a state, the policy pi tells me some probability distribution, and then I follow that, the environment undergoes some transition, and then I keep acting. So I get some, so the sequence of states, and therefore the discounted reward is some random variable, and I can take the expected value of that. That depends on the policy, and I want to choose a policy which maximizes that expected discounted reward. So that's the problem, to determine that policy. And that's a difficult problem for a non-trivial MDP, but to formulate the theory of even the existence of such a thing, well, in the way I've stated, it exists by the extreme value theorem. It's fairly trivial, but to actually find a way to construct that policy, it's useful to introduce the notion of a value function. So a value function is just a real valued function of states. It's again, these functions form a metric space with a submetric. Okay, so here's the interaction between policies and value functions. So for the reasons I just sort of elaborated, if I fix a policy and I tell you a state, you can look at all trajectories or sequences of states starting with that given state, and you can look at the expected value. I mean, these trajectories are generated choosing actions according to pi. It's not in the notation, but that's what that means. So this is the expected value of the discounted reward following the policy pi from the state S. And here, in all of this, you should think of states as being configurations of the Go board, actions being moves, and the reward being win or lose. I'll detail that in a minute. Okay, so that's a well-defined function, but it's useful to characterize it as a fixed point of some operator on this space V of value functions. So if I fix a policy pi, then phi sub pi is this expression here. I claim that function has a unique fixed point, and that fixed point is V sub pi. Okay, so operators like this will sort of be the key to the rest of the story. So let me talk through the right-hand side briefly. So I'm given a value function, and I'm going to compute a new value function, which evaluates the state S to be the reward I would get in state S plus, well, the discounted value of the expectation, given I'm acting according to pi, and that I make the transitions according to p, of the value function of the next state. Okay. So the idea here is that the value function, this is just some random function v, doesn't necessarily have anything useful to do with the game. So it might be inconsistent in some sense with respect to the reward structure and the transitions, and this is propagating information about the states to one another in such a way that once that process is completed, you've actually reached this value function v sub pi. So to prove the theorem, you just observe that, so this is a complete metric space, and you can check this function is a contraction mapping with contraction factor gamma. So by the Banach fixed point theorem, it has a unique fixed point. And then if you just look at the equation for this to be a fixed point, you can convince yourself it is given by this formula. Okay, so this is the organizing picture of reinforcement learning. I've got a fixed MDP. I've got a space of policies, a space of value functions. I can take a policy and see what it says about the value of every given state by taking this fixed point. That's sometimes referred to as policy evaluation. I can also take a value function, and if I think of that as giving me a good opinion about the value of certain states, I can choose to act according to that value function. Right? And that's what's called the greedy policy. So what it says is, so pi sub v is the greedy policy acting according to v. And it says, if I'm in state S, so this argmax just returns the action which maximizes this term here. So pi vs is a probability distribution over actions, but it just has probability 1 for some particular action. And it's the action which makes this expected value of the value function as high as possible. Right? So act as if you want to get the highest value of v. So that makes sense. Okay. So the goal, as I said, is to find an optimal policy. So here's the definition. A policy pi is optimal if v sub pi dominates v sub rho for every policy rho. And by this inequality, I mean v sub pi of s is greater than or equal to v sub rho of s for all s. Okay, so how would I find such a thing? Well, how would I prove it exists, and how would I find it? Well, recall there was this contraction mapping phi sub pi on v, depending on a policy pi, and here's a version that doesn't depend on any policy. So it's the same formula, but rather than take the expected value according to actions with respect to pi, I just say do the best thing. Right? Take the supremum over all actions of the expected value of v. And so this thing's called the Bellman operator. So the proofs that this is a contraction mapping is the same. So again, by the fixed point theorem, it has a unique fixed point, and then you can check that this v star, the fixed point, is greater than or equal to the value function of any policy, and therefore, if I look at this v star and extract the greedy policy, call that pi star, then that is an optimal policy. Okay, so here's a picture of, a completely infeasible but theoretically attractive way of solving any MDP. So I give you the MDP. Remember, the fixed point theorem says not only that a fixed point exists, but in principle it tells you how to find it. Namely, it says pick any point you like in your vector space, hit it with your contraction mapping, do it again, do it again, do it again, and eventually that iteration converges to the fixed point. Okay, so you take your MDP, pick any value function you like. It could be identically 0. Hit it with the Bellman operator and take that limit. At the limit, you've got v star. Extract a policy from that v star, pi star. Play according to that policy, and you cannot be beaten. Right. So that's, in principle, what you want to do. Now, in practice, you can't actually compute that iteration. For various reasons. I'll talk that through the reasons in the case of Go in a moment. But reinforcement learning contains a bunch of ideas and algorithms for approximating this fixed point iteration. So this fixed point iteration is a useful organizing principle in the same way that, the applied mathematicians can tell me, but probably you don't use Picard iteration to actually solve ODEs. But nonetheless, that's an important application of the Banach fixed point theorem to prove that solutions exist by this Picard iteration method. So that's a useful theoretical organizing fact, even if in practice you don't actually do that. Okay, so that's in theory how you would solve an MDP. Unfortunately, that still isn't good enough for Go, because Go is not an MDP. Why? Well, in an MDP, Markov decision process, you have an agent and you have an environment. And the environment is fixed. It might be stochastic, but it's fixed. And this process allows you to take an agent with a policy and improve that policy to become optimal against that fixed environment. But if I'm playing Go, okay, well, if I already have an optimal opponent who can sit there and play against me, that's a fixed environment, and indeed that's an MDP, and I can get better and better against that optimal opponent. But of course, the whole point is you don't have that opponent to start with. So, at least as formulated here, this is the wrong operator to try and iterate to find a solution to Go. But there's a slight tweak to fix that, literally some signs, which I'll go through now. So a Markov game, or alternating Markov game, is just an MDP, but with some extra data, which is a decomposition of the state space as a disjoint union of S0, which I'll call even states, and S1, which I'll call odd states. And the parity of a state will be written as bar S. So the idea being there's two players, the even player and the odd player, and S0 are the states in which the even player gets to play, and S1 are the states in which the odd player gets to play. We make the restriction that the transitions change the parity. And in that case, a policy which maps all states to distributions of actions is really two policies, right? One for the even player and one for the odd player. And we think of the reward as being the reward for the even player in that state. And it's, I want to talk only about zero-sum games. So the reward for the odd player is always minus RS. Okay, so this just formulates Go as a Markov game. It's basically, as you would expect, except for two sort of subtleties. So the first is this 8 that I mentioned already. So the state space of Go has this 0 or 1 there to say whose turn it is. That's necessary because you can pass. Here you need to specify whether a junction is either empty, white, or black for 19 squared positions on the board. and you want to specify it not just for right now, but for 7 previous turns. Okay. So a state is this S0, the current board configuration, through S minus 7, and the parity P. So that's the one subtlety. The reason for the 8, technically speaking, it needs to be at least 2. You need to remember the current state and the current configuration of the board and the previous one. The reason for that is the co-rule, which is a rule which forbids repetitions. So you can't play so as to repeat exactly the same state of the board as was before. And that means in order to know which actions are allowed, you need to know what the previous configuration was. So that's why you need at least 2 board configurations. I think anything above 2 doesn't seem to have anything to do with the underlying Markov game, but more to do with the training process of the algorithm, as far as I can tell. The rewards are only non-zero for the terminal configuration, where they're +1 if black wins. Black is the even player, and -1 if white wins. Okay, so most states have 0 reward. Okay, so we still have this picture. So this was the picture for an MDP, and I want to explain the refinements necessary for a Markov game. This picture is the same. So the space of policies and value functions is just the same for the underlying as for the underlying MDP. The mapping of policies to value functions is the same. It's the fixed point of the same operator. But what we had before doesn't actually make sense now. So remember what we had before was, so if I give you a policy, and I took the greedy policy, well, if I put in an even state, that would say, act so as to maximize the expected value of V. V is meant to be a proxy for the reward, so that would say, act so as to maximize the reward, or that is, maximize the even player winning. So obviously that's a good idea if you're the even player. You should play so as to maximize the probability you're going to win. But if this state is odd, so it's the odd player's turn to play, then you don't want to choose a move so as to maximize the probability of the even player winning. You would actually prefer to minimize the probability that the even player will win. So if S is even, you want to take the argmax of the same expression as before, which will be the case in this formula because this will be 0. But if S is odd, you actually want to minimize this, but the argmax of the negative is the argmin. Okay, so this pi plus or minus, which I'll call the graded greedy policy, just does sort of reasonable thing. Yeah. Okay. Okay, so that's how to extract a policy in the Markov game. So now there's a version of the theorem I stated earlier. So it says that given a Markov game, I've got this graded Bellman operator, which again is the same as what I had before, except for some signs, hence the plus or minus. This is the sign that we saw in the graded greedy policy. There's an extra sign here, which makes sense if you think about it, because if S is even, this is just the same formula as before for the Bellman operator. If S is odd, then I'm going to take a supremum of a bunch of negated numbers. But if I take the supremum of a bunch of numbers, that's minus the infimum of those numbers. Right? So the odd player wants to take the infimum, but this minus sign is not correct, so I just cancel it with this extra sign at the front. Okay, so that's also a contraction mapping, and therefore has a unique fixed point. And then you can prove that unique fixed point is what's called the Nash equilibrium of the Markov game. So for a Markov game, the notion of optimal is more subtle. It's not simply that this is the best possible policy that will defeat all other policies. So to explain what the Nash equilibrium means briefly, so think about extracting the greedy policy from this fixed point V star, call that pi star. That gives a policy for both the even and the odd player, pi star I. To say it's a Nash equilibrium is to say the policy pi 0 star is optimal against the environment which consists of pi 1 star, this other policy, and conversely. And there's exactly one Nash equilibrium, and it's this one. Okay, so that's optimal in a more subtle sense. Okay, so that's the right notion for a Markov game. Again, it's impossible to actually evaluate this fixed point directly. And the idea of deep reinforcement learning is to plug in the first part of the talk to approximate this whole story. So that's what I'll now explain. Much of what I'm going to say would work for any Markov game in principle, but of course, you know, they only spent the money to do it for Go, chess, and shogi. Okay, so to connect the two parts of the talk, what I need to do is to connect the top row here, which was the Markov game story, to the bottom row, which is the neural network. So in the top row on the left, S is the state space of Go, and that's organized around these two functions, the policy and the value function. In the bottom here, I've got some continuous function from an affine space to an affine space, parameterized by some weights, now called theta. It was n before, I apologize. So those are the real numbers parameterizing the neural network. Okay, so the way to do it is just to pick some way of embedding this discrete set into an affine space. The way you do it's not so important. Maybe I'll skip it. But you just choose some encoding. For instance, I mean, I'll just say briefly, instead of saying empty, white, or black, which could be like 0, 1, or 2, instead what they decide to do is two binary choices. Is this empty or white? And is this empty or black? Okay, so that's how the encoding works. And then, to approximate a policy or value function, what do I mean by an approximation? Well, I'd mean a neural network, so some function like this, such that if I take the state, I embed it as a vector, I evaluate the neural network on that vector, I take those real numbers and use them to parameterize a probability distribution. Machine learning people call this a softmax. Maybe you call it a Boltzmann distribution. So you parameterize the probability distribution, and this is just the identity in the second factor. And you'd say the neural network approximates a given pi and v if this diagram sort of almost commutes. So it commutes up to some small error. So that's the notion of approximation. Okay, so here's the strategy. We're going to take policies and value functions. I mean, I say we, the authors of the AlphaGo paper. Take policy and value functions, approximate them by neural networks, and try and project the Bellman iteration onto those approximations. And then do the iteration and, yeah, spend lots of Google's money. But it's okay, they have fountains of money, so. Okay, so this is a recap of the picture. Space of policies, space of value functions, Bellman operator. V is this function which just extracts a value function from a policy. P is the graded greedy policy. And the fixed point, the Nash equilibrium, is V star. Okay, so the bubble on the left is P, and the bubble on the right is V. Take some value function. I can then extract anything you like. Could be the zero function. I can extract a graded greedy policy from that, call that pi 0. So this is just the Bellman iteration to the fixed point. And so I apply phi plus or minus, that gives me V1. I could extract a policy from that, and so on. Okay, all the way down to optimal play for Go. Now, the point is you can't do that. So the state space of Go is, I meant to look it up again, but it's something like 10 to the power of, it's certainly bigger than 200, I think. So anyway, it's a very large number. 360, thanks, yeah, good. Okay, so you can do a little calculation. If you even wanted to store the value function, that is a real number per state, well, converting the entire solar system into hard drives would just make a tiny dent in that. So you're not going to be writing down the value function, let alone computing on it. So this is just completely intractable, what I've presented here. Okay, so we have to approximate. So the space of all value functions has this dense subspace of ReLU networks. So we can approximate V0 by V theta 0 and pi 0 by pi sub theta 0. And, well, obviously you could just go through and approximate V1, V2 up to V star, but the aim is to not to try and produce, not to approximate this by this and this by this, but to figure out what process we have to do to stay entirely within this gray zone, which, say, fits on our computer or cluster of computers, more realistically. Okay. So I'll talk you through the various approximations that they came up with to do that. So suppose we have some rho that we've already figured out. So that is some parameters theta I, which parameterize a neural network f theta I. And the, maybe I didn't stress this back here. So given one of these neural networks, it has two outputs, right? A policy, pi theta, and a value function of v theta. Okay, so given that we've got some values of the weights theta I, we can train the next iteration. So the iteration number is I. We can train the next iteration by applying the Bellman operator to v theta I to improve the value function by one step. That's now something that's escaped from the gray region, so it's no longer perhaps, literally a neural network, but I can then approximate it by some neural network, v sub theta I plus 1, let's say in the subnorm. And similarly, I can take this iterated value function, extract a graded greedy policy from it, and try and approximate that by a neural network. So in principle, that's what we want to do. And if you take these errors to go to 0 faster than the powers of the discount factor gamma, you can do a little calculation, convince yourself that that'll work, that the v theta i's will converge to the fixed point, and so will the pi sub theta i's. Yeah, maybe I should make a comment on the discount factor. I mean, it's important that it's less than 1 for any of the theory to work. But nonetheless, if you look at the AlphaGo paper, they'll say gamma equals 1. Okay, but that's fine, because you can take gamma to be 1 minus 10 to the minus 65,000, if you like. The computer thinks that's equal to 1, and we're all happy. But in principle, gamma should be a number very close to 1 for this. Okay. So what's the problem with this story? The problem is we can't actually evaluate this Bellman operator. That's one problem. The other problem is we can't evaluate this norm, because that's a sup norm, and it's a sup over all states of Go, which is too big. Okay, so there's at least 2 reasons why this is infeasible still. But they found a way to approximate both of them. Okay, well, if you were going to approximate an expensive thing, you might as well approximate d times the expensive thing, for the following reason. So remember that if you have a contraction mapping, any power of it is also a contraction mapping, and the contraction factor is the appropriate power of the original contraction factor. So any power of a contraction mapping will converge faster than the original one. So this is still a contraction mapping, and it converges faster, and for that reason it's a good trade-off for actually getting your algorithm to converge. So let's take d to be some power. Maybe try and explain what d is correct. Okay, so replace phi plus or minus by phi plus or minus to the d, and then we need to figure out some way of approximating both of those. And that's where the other ingredient in the paper comes in, which is Monte-Carlo tree search. So phi plus or minus d is replaced by this approximate dth power of the Bellman operator. So let me briefly explain what the idea is there. So if you remember, phi plus or minus, the formula for it, had this supremum in it over all actions. Now the number of actions you can take in Go is not so big, it's 19 squared plus 1. So that doesn't seem so impossible to evaluate. But if you iterate the Bellman operator twice, then you're taking a nested supremum of a supremum, both over that many actions. And if you do it many times, that's suddenly a very large number of sequences of actions over which to take a nested supremum. So the idea of this approximation is to say, okay, I'm trying to take a supremum over sequences of actions. I need to truncate that somehow because you can't actually compute that supremum. So you need to pick out some subset of sequences of actions which you believe are likely to contain the supremum in order to estimate the supremum. So how are you going to, at stage I of this process, come up with a way of determining which sequences of actions are likely to contribute to the supremum? Well, you've already got a policy and a value function at stage I. Right? You know pi theta I and v theta I. So they contain the information of some opinion about what moves are good and what states are good. And the idea is to use that current knowledge to perform that estimation. So use the current state of pi and v to evaluate which sequences of actions are likely to contribute to the supremum or not. And that's a rough description of the Monte-Carlo tree search algorithm. The details, it's a very important algorithm, but I'm not sure it's particularly canonical, so I won't present the details of the tree search there, but that has a long history, so that goes back to, someone can correct me if I'm wrong, but in a sense back to von Neumann's minimax theorem, and then the ideas in linear programming and dynamic programming and alpha-beta search and so on. So this idea has a long history for approximating these kinds of tree searches. So they perform that approximation, so to replace phi plus or minus d by this Monte-Carlo tree search version. And they do that also, the same data structure gives you an approximation for this extraction of the graded greedy policy. Okay, so that fixes the one problem, and then we've still got left this norm that we can't evaluate. But that's easier to deal with because if you want the L infinity norm to go to 0, you might as well make the L2 norm go to 0. And remember, these things are probability distributions, and if you want, the norm I had before was just literally measuring the difference of the probabilities, but you could instead use the relative entropy, which will be 0 if and only if these probability distributions are equal, so you can try and minimize that. And the advantage of these, I won't say metrics, because that's not a metric, but the advantage of these quantities is that you can estimate this. So remember, both the things here are real valued functions of states. Right? So this L2 norm means a sum over all states, the square root of the sum over all states of this minus this squared. So I can estimate that by choosing some subset of states. So I can estimate this by choosing a set of states, and similarly I can estimate this by choosing some set of states. And so, well, where are we going to get some large collection of states with which to estimate these distances? Well, we should just play games. So this is where the self-play aspect of AlphaGo comes from. So per iteration, they play 25,000 games of the system against itself. That generates many states. And from that, they get estimates of these distances. Those distances give rise to gradients, which you can follow to train the next iteration of the neural network. Yeah, I'll say something about that in a second. So that's the algorithm. That's how we project the Bellman iteration onto the space of neural networks. This is referring to the fact this is still not exactly what's in the paper, but this is cleaner, so it's what I'm presenting. And if you really want to know what I'm lying about there, please ask me afterwards. Okay, so in summary, first, the policy and value functions are approximated by convolutional neural networks. Then the Bellman iteration is projected onto those approximations. The two ideas there are Monte-Carlo tree search and self-play. And it works. So, well, Nobody says it gets to a fixed point. In fact, it's almost certain it's not at a fixed point. I can explain why if you're interested. But anyway, it gets to somewhere which is better than any human at Go, so maybe we shouldn't be too picky. So it certainly works to that extent. Okay, so the reason I chose to present AlphaGo is not because I particularly care about Go. Right? It's not why the scientists who did AlphaGo studied it either. The reason to be interested in this is that it's a new and interesting kind of program. And that those kinds of programs are characterized by a few sort of novel features. One is that at least part of them is differentiable, so varies smoothly with some vector of weights. Another feature is that the fundamental sort of unit of these programs is more like a tensor rather than a bit. And perhaps most importantly, but it's very hard to pin down exactly what I mean by this at the moment, is that these programs, they learn and compute with representations. So the idea here is that AlphaGo is this convolutional neural network plus Monte-Carlo tree search, and the convolutional part is doing most of the heavy lifting. Now, that's a quantitative statement because you can turn off the Monte-Carlo tree search part, and just the pure vision network is number 486 in the world, or something like that, if you look at the rankings. So it still plays very good Go. It's not better than every human. For that, you need the Monte-Carlo tree search part and look ahead. But just the straight-up vision network is already very good at Go. So the representation of the board configuration that's been learnt by this network is a very interesting object. And that's what I mean by a representation. So I think these kinds of programs are interesting for mathematics for various reasons. But perhaps the biggest impact will be in the other natural sciences. So these techniques, not exactly AlphaGo, but deep reinforcement learning and deep learning more generally, are making some headway on interesting problems from areas chemistry, protein folding, engineering complex quantum states. So I've put survey papers about all three of these at the end of the lecture notes. Maybe this is particularly interesting if you've sort of thought about strongly entangled states. Okay, so mathematically, I listed a couple of questions at the beginning, one of which was, why do deep learning networks actually work? Why do they, so I should go back to this slide and explain why this is a bit of a miracle. This sort of converges to something that's very good at playing Go. That's surprising because if you look at the theorem I stated at the beginning, which as far as I know is state of the art, if you make those, the depth you need to take is exponential in 1 over this epsilon. So in principle, according to our current theory, to make this go to 0, in order to get this to work, you'd need the depth of your network to go to infinity very quickly. But the depth is 42. Right? It doesn't increase over the course of training. And this distribution that this network is trying to fit to is shifting over the course of training. So it's not even a fixed distribution this thing is trying to fit to. So it's quite surprising that nonetheless it seems to work. So I think we don't really understand why. So there's some preliminary work in the last couple of years. I've listed some references at the end of something called the neural tangent kernel, which is maybe the best, as far as I can tell, best guess people have for describing why these things work at the moment. So in general, I think it would be great if there was more interaction between mathematicians and deep learning practitioners in Australia. There is some talented people doing this stuff here. And if you download the slides, that's actually a link that'll take you to a bit of a list. And look up your local expert, which is not me. But yeah, so I find AlphaGo to be a very interesting example of this new class of program. And thank you.